Here we'll talk about the alternating series test. Alternating series in general are cool, but we're going to focus on the case where there's a simple test to assure that the series is convergent. So by an alternating series, we mean a series where the signs strictly alternate between plus or minus. And one way to write that down and ensure that from the start is to take a sequence of positive terms. So the b sub n are actually greater than 0. Equal 0 would be fine, but it just complicates how you write things a little bit. And then artificially put an alternating sign in front of it. This could be minus 1 to the n, or minus 1 to the n plus 1, or minus 1 to the n plus 3, or whatever. This just has to alternate. This is nice if we start with n equals 1, this starts positive. But there's nothing really important about that. The main thing is the signs of these strictly alternate, and it's really important to use the tests for alternating series. Otherwise, it's a series with interesting signs, not an alternating series. So let's assume two more things about this series. I'm actually going to show you a sketch of the proof of the alternating series convergence test. One is that the terms strictly, well, they get smaller. They can stutter and equal each other sometimes, but they consistently get smaller as n goes to infinity. And that's actually very important. If you don't have that true, you can have all the other conditions be met and not have convergence. And the second condition is simply something we know has to be true, that the limit of the terms goes to 0. We know that this was what we refer to as the divergence test. The first thing you ever look at, almost, for any series is whether the terms themselves go to 0 at all, much less fast enough. And if they don't, you just throw it out. It's like it's not going to converge as a series. So almost what the alternating series test says is that as long as this is true, and it's alternating, which is going to be pretty visible, and another easy thing to check, and you do have to check it, but it's usually pretty easy, that the terms decrease to 0 in size, then I claim the sum of this alternating series is convergent. And this is a big deal because it means that it's much easier for an alternating series to converge than a series of positive terms. This is not a super hard requirement, although you do have to check it. And this is the requirement that you always have. But this was much too weak in general to guarantee convergence for a series of positive terms. There's plenty of sequences of terms that go to 0, but not nearly fast enough so that the sum converges. But when you put in alternating signs, you get lots of cancellations, and it becomes much easier. So here's the picture. It's similar to pictures in just about any calculus book, for Stewart, for example. So here's a picture of the partial sums of such a gadget, Sn. So here's S1, which is just equal to b1 times plus, so it's just b1. Okay, so that's the first thing. Now, the next one is going to be S2 is b1 minus b2. So I want to think of it, you've gone from 0, you added b1, and then you subtracted something, something smaller. So you haven't gone negative, and you haven't gone very far from where you started in particular. Okay, so we're already using this a little bit. Now this one is S3. That's b1 minus b2, then back with the alternation to plus b3. So we go down and we consistently wiggle down and then guaranteed up and up by a smaller amount. That's where this is used. We don't go as high as where we were because the difference b3 minus b2 is going to be, that's a negative number because this guy is decreasing, and so the net change from b1 to including these two has actually gone down. So basically you just want to think of it as we're bouncing, and every time you bounce, you don't bounce as far, and so you're going to get a decreasing wiggle. You're guaranteed to get qualitatively this picture. Nothing really qualitatively different. So you're going to get this bouncing up and down, and so in particular, if you just look at just the odd terms, then that's going to be a decreasing sequence. Great. The only way a decreasing sequence can diverge is if it diverges to minus infinity. But wait, they are bigger than the even terms that are interlaced between them, and those guys are going up. So you've got this upper envelope, the red ones, the odd terms, and the lower, the green terms, and they're converging seemingly towards each other and trapping the actual limit in between them. Now, is that really true? Well, here's where we use the fact that the size actually does go to 0. you could have something, if you didn't have that last condition, you could definitely have a picture where the odd terms were going like this, and the even terms were going like this, and there was a fixed gap in between, and it never got smaller. And you just got oscillation, and that's not convergence. But the fact that the size of the terms is going to 0 means the size of the oscillation gets small, and they are going to converge to a limit. If you want to see that more precisely, that's what the book's for. Okay, but it's a pretty nice idea. And I want to just use that right now. Our book separates it into 2 statements, but I want to show that this gives you a very easy remainder bound. Remember, we always call the remainder, that's the actual sum, the limit of the partial sums, minus the nth partial sum. And it's nice to get a bound on that. Well, let's see. The size of that, let's not worry too much about whether we're overshooting or undershooting, although we can tell from this picture. But just in terms of the size of that, let's say I stopped after S3, for example. If I stopped after S3, then the very next thing I would have done is gone down to that green guy. I know for a fact that's below the actual eventual limit, because all the greens are below, all the reds are above. So putting in even one more term going down overshoots. That means the real error, which is just this difference here, has got to be smaller. So this is smaller than or equal to the size of the next term, the first discarded term. This is the simplest. Oh, we got some interesting light effects coming in here. This is the simplest kind of error bound. And often people use a very rough version of this when they maybe shouldn't. But for alternating series, it really works. That the difference between the ideal limit that you may never actually get and your nth partial sum, which you might get just by cranking out 10 or 100 or 1,000 terms on a calculator, the difference is going to be smaller than or equal to the next discarded term. And that's really nice. So the first classic example that everybody gives here, I'm going to give 2 quick examples. I don't want to make this too long, and I'll have a part 2, is the alternating harmonic series. Just a classic series. So the regular harmonic series is the sum. You might have noticed I've switched back to n, but whatever. I still like k a lot. That's the harmonic series. We know that diverges. That's not alternating. But the sum, if I put in signs, and let's just have it with the n-1 convention so that it ends up starting with plus, that converges. Because here the b sub n are just the harmonic terms. They're just 1 over n. Those definitely decrease to 0. And they're positive, so when you alternate them, they really are alternating. And so it satisfies the alternating series test. So that's pretty cool. Now, the harmonic series is it diverges really slowly. It's fairly close to being something where these terms go to 0 fast enough to converge. And so this isn't demonstrating too much the incredible help that alternation gives you. Something that demonstrates it a bit better is still a really important example. And a cool thing is, fairly soon we'll be able to figure out what the actual sum of the alternating harmonic series is. It's a very nice special number. Oh, okay, and now I think I'm blocking the light better. Let's take, for example, 1 over the natural log. I don't want to do n, because then I'd have 1 over log 1, 1 over 0. But let's just n plus 1. Okay. This guy diverges horribly. It's true that it still satisfies the fact that the terms go to 0. Because the log goes to infinity. So 1 over the log goes to 0. Okay. So if these are b sub n, then yes, they go to 0. But boy, they go to 0 slowly. For example, log of like 1,000. That's a pretty big number. That's only about 7. And so you've added up 1,000 terms. You're still only at about 1/7 here. This just diverges very, very horribly. It's not even really trying very hard. But these terms, we know that b sub n plus 1, that's 1 over the log of n plus 2. Yes, that is actually strictly less than the log of n plus 1, the 1 over the log of n plus 1, and that's b sub n. So it's decreasing. The sizes are strictly decreasing. They don't play funny games in terms of getting bigger than smaller in a weird way. Okay, and they're definitely all positive numbers, and they are going to 0, and so if I alternate them, it actually is going to converge. Okay, so this one converges, and that's a big difference. It was not even trying, and now it actually does converge when you put in the alternation. So in the next one, I'll show an example of using that error bound for the alternating series, and that's really, really useful.